Hello. Just can one of you please confirm if I'm audible?
Yes, sir, you're audible.
Okay, thanks. Then let's start it. Yeah. Last class we started corsets. I mean, just take a 5-minute revision of where we are. Okay. So what is a resource element group? A resource element group is a resource block across one slot. Across one symbol. Okay, that was 12 RE. And we have defined a control. We have defined a control channel element as consisting of 6 REGs. Okay, 6 REGs means 72 resource elements. 12 into 6 is 72. Okay. So this also contains pilots, and there is the mapping of the CCE to the REG happens to something called as REG bundles. That's what we are going to see later. Okay. So what is an REG bundle? So we have understood also how to number the CCEs. So how to number the REGs. First, it goes through the increasing symbols and then increasing frequency 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so on. Okay, if there is one more thing, it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on and so forth. Okay, so we saw that last class. So what is an REG? What's an REG bundle? So REG bundle is a collection of REGs, okay, a contiguous set of REGs. Okay, so this REG bundle size is defined by the parameter L. Here in this particular case, I gave an example of L is equal to 6, 0, 1, 2, 3, 4, 5. Okay, and the next 6 are the next REG bundle, and the next 6 are the next REG bundles. Okay, so REG bundle need not have 6 REGs. Okay, it can have something less also. Fine. Okay, then okay, but how you define? I mean, the parameter L comes from the higher layer parameters. Okay, that L. Okay. So the question is now, how do you map CCE? CCE always consists of 6 REGs. Remember, CCE always consists of 6 REGs. Okay, a control channel element. So how do you map a control channel element to one REG bundle or a set of REG bundles? Okay, because an REG bundle may consist of less than 6. So what might happen? You might have to map it to maybe more number of REG bundles. Okay, so how do you do that? Okay, so that depends on two parameters, whether the mapping is called interleaved or non-interleaved. Okay, so why do you use interleaved and why do you use non-interleaved? So non-interleaved means essentially the CCE, for example, if for example REG bundle consists of only 2 elements, L is equal to, so then this will REG bundle 0, 1. It will consist of 0, 1, 2. Okay, so then what will happen if you map all the 3 REG bundles to one CCE? Then all the REG bundles are contiguous. So if they're contiguous, what might happen? Okay, if something is contiguous, what will happen? Suppose there's a deep fade because of some deep fade. So your channel may become bad in some contiguous set of frequency bins. Then that complete REG bundle and the complete set of REG bundles and the complete set of CC will get completely you will receive them in errors. Okay. Instead of that, what you can do, you can put you can put this one REG bundle from here and one REG from here, one REG bundle from here into one CC. Okay. Then that data of those 3 things will be protected by a single error correction code, one polar code. Okay. So then what will happen? Even if one of the REG bundles was in error, the other REG bundles may be good because they separate out in frequency. You get the frequency diversity. Because of that, you might be able to hopefully recover data because of the frequency diversity. Okay, so that's why there are 2 options. One is called interleaved, another is non-interleaved. Of course, interleaved is complicated in terms of implementation. This non-interleaved is very much more straightforward. Okay, did you understand these 2 notions of REG bundle to CCE mapping, interleaved and non-interleaved? Okay, so this is again given by higher layer parameter called CC REG mapping type, interleaved or non-interleaved. Based on that, you have to do your mapping. Okay, any questions here? Okay. So what it says is, this is the equation it says. Let's just understand this equation. You will see some kind of similar equation and other things also. So it's good to know this once. the CCJ, okay, so essentially this means I mean, we're trying to figure out which REG bundles is the jth CCE mapped to. It says the jth CCE is mapped to how many REG bundles will be there? Remember this. So if L is equal to 6, how many REG bundles will be there? Each CCE will map to how many bundles? Can anyone tell me? Hello. See, remember, every CCE consists of how many REGs? 6 REGs. 6 REGs. So if your REG bundle itself has 6, then each CCE will consist of only one REG bundle. One REG bundle. On the other hand, yeah, if your REG bundle has L is equal to 2, then how many REG bundles it will have? CCEJ will have 3 REG bundles. Okay, because the CCE will always have 6 REGs. Okay, the size of the REG bundle might change. Okay, so that's why they said, if you look at this equation, they said every jth CCE is mapped to so many REG bundles. Okay, so the number of these things is 6 by L minus 1. It starts at 0, this plus 0, so 6 by L. Okay, so if you have L is equal to 6, you have only one REG bundle it's mapped to. If you have L is equal to 2, it will be mapped to 1, 2, 3 such things. And this is given by f of 6j divided by L. Okay, this f is the function that we have to determine what it is. Okay, so this f of x, sorry, 1 minute. In the non-interleaved case, what happens? F of x is equal to x. That means it's an identity map. So what will happen? J will be mapped to f of 6j by L. F of 6j by L is equal to 6j by L. So essentially what will happen, if L is equal to 6, it will be mapped. So if L is equal to 6, this 6 and 6 gets cancelled. So it will be mapped to f of 6j by L is equal to j. So J0 CC will map to 0th bundle. First CC will map to first bundle. Second CC will map to second bundle. Is this clear? Okay, so let's take the case of L is equal to 6. L is equal to 6. Okay, so essentially what will happen? The jth CC will be mapped to f of 6j by L, f of 6j by L plus 1, so on, f of 6j by L plus 6 by L minus 1. Okay, so let's simplify this first. So L is equal to 6 first. L is equal to 6 means essentially it is f of 6j by 6. It will be j, f of j plus 1. So how many are there? F of j plus 6 by L minus 1, 0. Okay, so essentially this is only, this whole set says there's only one element. This is not even there. Okay, so it is only, this is whole thing for L is equal to 6 will be f of j. Okay, so j will be mapped to f of j. Okay, so in the non-interleaved case, f of x is equal to x. So it's an identity map. Whatever you put as input will come as output of f. Okay, so j will be mapped to j. Is this clear? Fine. Okay, so the 0th CC is mapped to 0, 1 is mapped to 1, 2 is mapped to 2, and the 0th bundle will have 6 such REGs because L is equal to 6. Okay, so on and so forth. Is this clear? Is this mapping clear? So this does not provide you enough frequency diversity. Okay, so now let us look at the interleaved mapping. Okay, so this interleaved mapping, while the equations look very, very disturbing, it's actually a pretty simple mapping. It is called block interleaving. Okay, so what is block interleaving? First of all, what is interleaving? Interleaving is nothing but, what is interleaving? If you have 1, 2, 3, 4, you pass it through an interleaver. What do you get? You get a jumbled out version. Okay, maybe 3, 1, 4, 2. Okay, So if you have an interleaver, you will also have an interleaver inverse of the interleaver, so that when you pass this to the inverse of the interleaver, you get back 1, 2, 3, 4. Okay, there are so many types of interlevers are there. Okay, in error correction code, interlevers are very, very common, specifically in turbo codes and other things. Here they use something called as a block interleaver. Okay, so what is a block interleaver? Okay, suppose you want to interleave 1, 2, 3, 4, 5, 6, 7, 8. Suppose you want to interleave these 8 numbers. Okay, there are so many ways to interleave. Any permutation of this number is an interleave. Okay, so in the block interleaver, what you do is, suppose you first fix the size of a matrix. Okay, in this case, I'll assume that there are 2 rows in the matrix. If once there are 2 rows, if there are 8 elements to interleave, there will be automatically 4 columns. Okay, so the number of rows is equal to 2, so automatically 4 columns will be there. Okay, or you fix the number of columns and the rows will be fixed. Then you write them row wise. 1, 2, 3, 4, 5, 6, 7, 8. Okay, you write, so you're writing it row wise. You're writing the numbers row wise. Okay, but when you're reading it out of it, you read column wise. Okay, so the interleaved output will be 1, 5, 2, 6, 3, 7, 4, 8. Okay, so we have actually used this kind of interleaver already once. Okay, this is the interleaver that is used in the after you scramble your data, after the data comes out of your FEC, then you do your rate matching, then you do your code block combination, then you do an interleaver. Okay, you use a similar kind of interleaver there also, by the way, if you remember that. Okay, so this block interleaver is called a block interleaver. So you write row wise and you can read column wise. Okay, there are other things also where you write column wise and you read row wise also. Okay, in this particular case, you write row wise and read column wise. Is this clear? Okay, so that is the same interleaver that is being used in for doing the interleaved CG to CC. I mean REG to CCE mapping. Okay, of course they did. I mean they don't say it in simple words like this in anything in 3GPP. They write a big equation like this. Okay, so if you actually think about this equation carefully, this is nothing but what I told you. Okay, so what they are fixing, L anyway, you know, L is given by the REG bundle size. Okay. Okay, so then what you do, then R is the number of R is the higher layer parameters, is the number of rows. So once you know the number of rows, then you automatically know the number of columns. So you write it in row wise and read it column wise. Okay, that's the simplified version of this whole set of equation. Okay, I mean of course there's something called an N shift and other things you apply, but forget about those N shift for now. Okay, I'm just taking an example here. Okay, so the number of RBs in the corset was 24. Okay, number of symbols is equal to 2. Okay, so you have 2. I mean, anyway, these are irrelevant parameters to this. So you have L is equal to 6, R is equal to 2. Okay. So how many first of all, how many REGs will be? I mean, resource block. How many REGs total REGs are there? Can anyone tell me? The 48 REGs.
2, sir. 2.
No, the 24 RBs and 2 symbols. Okay. So the number of REGs are 48. 24 into 2 is 48. Okay. So number of REG number of CCE will be, how many CCE will be there in this? 48 REGs means how many? By 6. 8 REGs will 8 CCEs will be there. Okay. So 8 CCEs we have to now map it to the REG. So let's see what is the REG bundle size. Here we have taken the REG bundle size to be 6. Okay. So let's do this. Let's just do this properly. I'm going to write it on my laptop. Okay. So you have 1 minute. Okay. So you have 48 resource element groups. Okay. Number of CC will be equal to 48 by 6, which is equal to 8 CC will be there. So there will be a number from 0, 1, 2 up to 7 CC. Okay. We have L is equal to 6. So number of REGs per REG bundle is equal to 6. Sorry.
Sir, your iPad screen not fully visible.
Yeah, sorry. I'll get it. 6. Okay. I'll write it small. Something, why is it switching off? Just hold on 1 minute, please. Okay, something happened and the software is crashed. Okay, so for weird reason it's not connecting, but I'll just make a slide and we can write this up. Okay. I'll just type it here and then 48 REGs are there. So number of CCE will be equal to 48 by 6, which is equal to 8 CCE. L is equal to 6, which implies number of REG per REG bundle is equal to 6. Sorry, number of REG. So essentially it means REG, number of REG bundle per CC will be 1. CC equal to 1. Okay, this is clear. Now this part is clear. Okay, now let us see the mapping. There is one more thing that we did. We said that the number of rows is equal to 2. Number of rows equal to 2. And number of REG, how many number of REG bundles are there? Number of REG bundles are also equal to 8 in this case, because each REG bundle has 6 REGs and there are 48 REGs, so number of REG bundles is also 8. Okay, so if you number the REG bundles as 0, 1, 2, 3, 4, 5, 6, 7, which is the case here. I bundle the REG bundles as 0, 1, 2, 3, 4, 5, 6, 7, and I put the REG bundles as increase. So as the number of rows is 2, so the number of columns will automatically become 4. So I wrote the REG bundle numbers here, 4, 5, 6, 7. Okay. So now what will happen? Then the CC0 will map to 0, CC1 will map to 4, CC2 will map to 1, CC3 will map to 5, CC4 will, CC4 will 2, 5 is this, 6 this, and 7 this. Okay. So that's how you do. You understood how I did this one now? So this is the REG bundle numbers I wrote. I wrote in increasing order like this. Okay. Then while reading out, this corresponds to CC0, CC1, CC2, CC3, CC4, CC5, CC6, CC7. Okay. So finally, when you write this map, 0 corresponds to 0, 1 corresponds to 4, 2 corresponds to 1, 3, 5, 4, 2, 5, 6, 6, 3, and 7, 7. Okay. So the bundles are all jumbled up. So this will not give you any frequency diversity, but we have to, if you do this with the case where L is equal to 2, suppose I would want you to do this example. Okay, so do this example with L is equal to 2. So if you do this example with L is equal to 2, what will happen? What will change? So the number of REGs in REG bundle is equal to 2. Okay. So each CC will have how many bundles? Okay. Let's do this example. Actually. Let's do this example. So now suppose I do L is equal to 2. So number of REG bundles per CC is how many? So each bundle has 2 REGs. Okay, and CC has 6 REGs. So the number of REG bundles will by CC per CC will be 3. Not divided by, I will put per CC will be 3. Agreed? Okay. So total number of REG bundles is how many? In this case will be 24. Okay. So we have to write both the rows. So let's do this. 1, 2, 3, 4, 5, 6. No, it starts at 0, 1, 2, 3, 7, 8, 9, 10, 11, 12. Okay. Then 13. Maybe not like this. Okay. Okay. So these are what this is now. These are what I wrote is the indices of the REG bundles. Okay. So let's see now. Let's write the mapping. So the 0th CC will be mapped here. The first CC will be mapped here. Okay. So in this particular case, number of CC will be 8. Always CC will be 8. Okay. So I'm going to write the map for the CC in this pack. So 0th CC will be put here. The first CC will be put here. Second CC will be put here. Third CC will be put here. Fourth CC will be mapping here. Fifth CC will be mapping here. Sixth CC will be mapping here. Seventh, eighth. Okay, seventh. After seventh, what will happen? 7, 0 to 7. Then again 0 starts. 0, 1, 2, 3, 4, 5, 6, 7. Again 0 starts. 0, 1, 2, 3, 4, 5, 6, 7. Okay. So now let us see what is the REG. Let's okay. So REG, I mean CC is 0 is mapped to what REGs now? Is mapped to the 0th REG, the 4th REG, and the 8th REG. CC1 is mapped to 12, 16, and 20, so on and so forth. Okay. So now you can see this. So now if these REGs are distributed, so now all these REGs are distributed across frequency. Now, so CC is 0 will have some frequency diversity because it's mapped to 0th REG bundle, 4th REG bundle, and the 8th REG bundle. CC1 is mapped to 12th REG bundle, 16th REG bundle, and 20th REG bundle. Is this clear now? Any questions? Is it fine? Am I audible?
Yes, sir. Yes, sir.
Hello? Hello?
Yes, sir. It is clear.
Okay. Sorry, there seems to be, I mean, I was not able to hear anyone. Were there any questions? Any questions? Okay. So, I mean, now you understand that for different number of CC, REG bundles and other things, you get a lot more frequency diversity or lesser frequency diversity. You can play around with all these things. Okay, this is called the interleaved mapping. So, interleaved mapping is very, very common. For example, when you do SIB1, SIB1 is interleaved mapping. So, you have chord set 0 is interleaved mapping. So, you have no other choice but to implement this thing. So, for SIB1, these are the things I gave for SIB1. This example is for SIB1. Okay. Example with the least. Okay. Okay. So now the question is, where do we put? So essentially, we understood where to put in the time domain. We also know whether a chord set is interleaved or non-interleaved. Okay. Still, we are talking about only the chord set. Remember that. Okay. Interleaved or non-interleaved. The question is, where is it put in terms of frequency resources? Okay. The location of the chord set in terms of frequency location is given by a 45-bit length string. Okay. So 45 a bit string of length 45. Okay, so you can see the frequency domain resources 45. So what does this 45 mean? Okay, so let's understand this. So it turns out what they do is every 6 RBs they put a 1 if that particular 6 RBs are present in the chord set. If not, they make it 0. Okay, so if you take 6 into 45 is equal to 270 RBs. 270 RBs is the maximum number of RBs that you can put. Okay, so what you have is this 45 bit string indicates what do you say? That's called the indicator function. It indicates whether a particular 6 RBs starting from CRB 0 is present in your chord set or not. Is this clear? Do you understand this? Okay. So this kind of also shows that your chord set need not be, I mean, it looks like it need not be contiguous in frequency. Okay, your chord set need not be contiguous in frequency. Because if it's contiguous in frequency, they can just give you start and stop. But unlike that, what they did was they put a bit string and said that if this bit is on, then the first 6 RBs are present. 6 RBs are present in your chord set. Next bit is 1, the next 6 RBs are present in your chord set. Next bit is 0, that means those 6 RBs are not present in your chord set. Is this fine? Understood this? Okay, so this is the main chord set resource information element. Of course, every chord set is specified by an ID, control resource set ID. Okay, and the frequency domain resources are given by this bit string of 45 length. Okay, and the duration is present by max chord set duration. You understand what is the duration now? Okay, and then it tells you what is the REG CC mapping type, whether it's interleaved or non-interleaved. Okay, if it is interleaved, it gives you the bundle size N2, N3, N6. All sizes are not possible because they have to be divisible by 6. They have to divide 6. Interleaver size is the number of rows, 2, 3, 6. And shift index is the parameter there. Shift index means everything will get shifted a little bit. I mean, let's not worry about that right now. It's not too much important at this point. Is this fine? Any questions on this? Oh, good. So we have already seen this DMRS for PDCCH for the core set. Okay. So we have already seen this in the sense that the useful number of bits per CCE is 108. Yeah, 108 bits per control channel element. Every control channel element has 108 bits you can use. Okay. We have already seen this part. This one is also something I told you earlier. PDCCH is a single port channel. Okay, so it's it's port 2000. Okay, but just let's discuss this 1 minute. Okay, this is kind of a important thing. Okay, so let's take an example of a 64 antenna system. Okay, 64 antenna system. Fine. So generally, DOT and other people, what happens? You put a maximum limit on the EIRP of the particular base station. Yes, you say, I think India, I think it is 66 dBm. EIRP is the maximum, if I'm not mistaken. Around 66 dBm, I think so. Okay. So you put it on the EIRP. So what is EIRP? EIRP means effective isotropic radiated power. Okay, so effectively what you do is you add the power that's coming out of all the antennas, and then you say that is the total power. Okay, good. That's very good. So if you look at the data path, PDSCH path, that data is going through multiple antennas. It is getting nicely beamformed. So it is actually having a lot of power to travel to longer distance. Yes, it's having a lot of power to travel because it's coming in multiple ports. Now, I mean, the data comes in multiple ports. You do your precoder and other things so as to beamform to particular directions or particular users. So it's all good. Okay. But if you look at PDCCH, it's a single port transmission. It's single port 2000 port. Okay. So what should you do? I mean, this is kind of a counterintuitive, but if you don't decode PDCCH, you will not be able to decode any data. You will not be able to decode PDSCH. You will not be able to, I mean, everything is a total waste. I mean, until unless you decode, one of the most important chance to decode is PDCCH, because only when you decode that, you know what are your allocations, what are the modulations to be used, everything. All the information is there. But why did they put a single port? Okay. Can you give any comments on this? What do we do? Suppose I'm building a massive MIMO solution, like what we are doing in the test bed. What do we do for PDCCH? Yeah, please. Any comments? Okay, so what you have to do is, while it's a single port transmission, okay, my iPad came up, so I can draw and nicely explain this. Okay, so remember what is happening with the data. Data, you are getting multiple layers, 1, 2, 3 layers. I mean, and then you put a precoder. Okay. And this precoder, what will it do? It will give out 64 antennas, or how many ever antennas output it will give out, or I mean, approximately. And you transmit. So this will nicely beamform into that user or this user, user 1, user 2, and so on and so forth. Okay. This is data. Okay. But control is one port. Similarly, SSB is also one port. Okay, remember, SSB is also one port. Okay. So what do we do with this? Why? So one thing we can do for this is, while it's a single port transmission, you can still apply a precoder. Okay. So what is the precoder you apply to most? I mean, because control channel is dedicated to multiple users. There's a common control. I mean, there's of course UE specific control also, but those bandwidth parts might be occupied by multiple users, and you may use the same core set space to do multiple users also. So one thing you can do is, instead of creating multiple narrow beams to different users or something, you can create a wide beam. Okay, you can create a wide beam. So in LTE, this was never a problem. LTE or anything, this was never a problem, because each antenna was outputting a lot of power. Okay, so for example, if the total output power was 40 watts, even if you transmit with one antenna, you get 10 watts of power. Okay, Whereas in this particular, if you have 64 antennas, each antenna can transmit at most like 1.5 watts or 1 watt. Okay, if you transmit in a big cell, you do beamforming and nice EIRP and transmit data channel so as to get 66 dBm. But if you transmit the control channel through only one port, means only one antenna, you will not reach anywhere. Okay, so for these control channels and all that, you have to do wide beam wide beam precoding. Okay, so you transmit them to all the antennas. While you get a single layer, you transmit them to all the antennas, so you get a wide beam, so that all the users can receive this control information. Maybe for a specific user-specific control channel, maybe you can do even user-specific beamforming also. Okay, this is something to keep in mind. Okay, so control channel design, how you do beamforming for control channel is a critical thing in 5G NR. In LTE, it was not such a big deal because there was enough power that is radiated from each antenna, whereas that is not the case in 5G NR. Okay, 5G NR, each antenna, because of massive MIMO, each antenna might put out only lower power. Okay, so you cannot just give that one port to one antenna and just be happy. You have to make sure that you have a precoder which spreads it out across all the antennas, and you get a wide beam. Okay, wide beam, of course, one disadvantage of wide beam is the coverage is less. Okay, but the good thing with this one, what do you say, control channel is it's heavily coded. Okay, it's heavily coded. The code rates are low. It's just QPSK. So the required SNR for decoding control channel is generally low, much lower than what we require for data. Okay, any comments on this? Any comments? Any questions or comments? Okay. Okay. So now we know what is a core set. Okay, core set is a collection of what do you say? A collection of time frequency resources, and you do the mapping. You define something called RDGs, then do RDG bundles. Finally, CCE. Finally, CCE is what is important, and each CCE is mapped to a set of resource elements in the core set. That's all you have to understand. Okay. TCCH is transmitted using CCE. Okay, so every control that you send, control channel that you send per UV or anything is transmitted through CCEs. Only it worries about only CCEs. It does not worry about REGs or anything, because CCE to REG mapping and the core set mapping is all defined well. We have done that now. The number of CCEs used per transmission of PCCH. Okay. So every user will have its own PCCH channel. Every user will have PCCH channel. There's common PCCH channel and all this. So every PCCH is transmitted using CCEs, and the number of CCEs used for PCCH is called the aggregation level. Okay. So if you I mean, this is something we discussed also. You have higher aggregation level if you use lower code rate because you want to transmit for a longer distance, or you have a larger amount of data. Either way, you can use a higher aggregation level. Okay. So up to 16 aggregation levels are possible. Okay, so your 16 aggregation level will correspond to 16 CCs. Okay, so 1, 2, 4, 8, and 16 aggregation levels are possible. Is this clear? So now we are moving. Essentially, where is this diagram I showed? Sorry, it's there in my iPad. 1 minute. Okay, so we finished this core sets. We understood the mapping of these core sets and other things. Okay, now we are coming to the aggregation level. We are just coming here. So essentially, we are thinking how these core sets are mapped in, how these different CCs are mapped into different core sets. Okay, subspace is something different. I'll tell you what that is. Okay, just will come back up to that in 5 minutes. Okay, so now CCE, I mean your formats, DCI formats are all mapped to a certain number of CCEs, and we know already CCE to REG mapping are other things in the core set, which physical locations they are there. Okay. Now what it turns out is that all CCEs cannot be occupied by all formats. That is what search space does. Okay, which CCE can be occupied by which format and other things is defined by the search space. Okay, we'll come to that in a minute. Okay, so this is the aggregation level and this is the number of CCEs. Just read out this slide. I mean, so it's called what are called the PDCCH candidates. It is a number of CC indexes searched by a UV in a subframe for a particular search space. Okay, we'll come to this in a minute. Okay, I think this is. I'm just going to this slide came outside the scope. Okay. So, any questions till now before I go into search spaces? So let's go into the search spaces. Let's understand what is meant by search space and other issues. Okay. So as I was mentioning, multiple DCI formats are possible. Okay, multiple DCI formats are possible, and multiple aggregation levels are also possible. Okay. So at the point when when the user is UE is trying to decode the DCI, but decode the PDCCH, it does not have any information. Only when it decodes this whole information is present in the DCI. Okay, so it has to do something called blind decoding. This is what I indicated. If it goes on blind decoding all the courses possible for all the search space, for all the formats and all the aggregation levels, it will take. The whole battery will be drained in a minute. Okay, and it's also very, very complicated also. So what they decided was, they said that we'll define something called a search space for a particular format or a particular type of transmissions. Okay, so the search space in some sense restricts the number of candidate control channels that the UV is supposed to decode. Okay, so for example, some search spaces you might have to decode only two control channels, or two candidates. Some such spaces you might have to decode four candidate control channels. Okay, so the search spaces help a UV in reducing the amount of complexity for decoding PDCCH. Okay, to understand this, let's understand a little bit of PDCCH. Sorry, maybe I'll move this a little bit down. Let's start. Okay, so there's 6 type of search spaces. Okay, one is called the. Did I put everything? Yeah. There are two broad categories. One is called the common search space, and the other is called the user search space. Okay, the common search space has 5 different types of different search spaces, and user search space has only one search space. Okay, so for example, this type 0 search space is used only for SIB1 messages. Okay, type 0A search space is used for other SIB messages, SIB2, SIB3, SIB4, SIB6, and SIB5 and other things. Okay, type 1 is for message 1, message 2, message 3. This is this one. Type 1 is a RA search space, which is a random access search space. Okay, so this search space is used for decoding control information pertaining to random access, which is PRACH. So type 2 search space is used for paging. Okay, so essentially this one, it's a common search space. So essentially paging means essentially it sends broadcast information to all the users. Okay, some particular broadcast information. There's another search space called type 3, which is a which is again a common search space. Again, UV common signaling, and I'm not very sure on what they send in type 3 actually. Okay, and this last search space, which is the UV specific search space, is mainly for UV data transfer. This is where the scheduling of particular UVs and other things happen. Okay, particular UV, if has to be scheduled, that is put in the UV specific search space. Okay, so there are 6 types of search spaces. Is this clear? And this is what 3GPP defines. Any questions on this? Okay. So in addition to this, so what did we see? We already saw that the number of card sets per bandwidth per UV is about 12 maximum. Okay, that's one thing that we have talked about when we started this whole thing. Okay. So even with this such number of, even when you restrict the search to search spaces, again, we'll understand this in a careful manner. The number of candidates, such as PDCCH candidates, that you should search for is very, very high. So what they said was the maximum, so to just reduce the complexity of UV implementation, they said that the maximum number of PDCCH candidates to be searched per slot is, I mean, depending upon the subcarrier spacing, is upper limited. So if you are doing, for example, 30 kilohertz, it says a UV will search at a maximum for 36 PDCCH candidates in a slot. It will not search more than that. Okay, so the base station should make sure that it does not send more than 36. Okay, so one thing that you observe is, as the subcarrier spacing is increasing, they reduce the number of PDCCH candidates. Okay, the reason is very simple. The reason is, as the subcarrier spacing is increasing, the slot duration decreases because the OFDM symbol size duration decreases because the latency is decreasing. Now that's what we saw. Okay? Inversely proportional to subcarrier spacing. Okay, so the UV has to finish the searching faster. So that is the reason why they reduce the number of PDCCH candidates per slot. As the Hello.
Your voice was not coming, sir.
Yeah. Sorry. My internet, my internet completely died. I mean, there was a power cut and the internet went away. So I'm just connecting by my cell phone now. Okay, I think we'll stop the class now. I mean, and next class. So next class we'll have it on Monday. Currently I'm in my Vijayawada. So next class we'll have it on Monday. Monday 9 o'clock we'll catch up, and we will do the search spaces and finish the search spaces on Monday. Okay, I'm going to stop now. There's no power and no internet here at this moment. I'm just connecting by my phone. Okay. So thanks. We'll meet up again, catch up on Monday morning, 9 o'clock. Is that fine? Monday morning, 9 is fine?
Yes, okay, sir.
Okay. Thank you. Thanks, everyone. Thank you.